Welcome to the course on FPGA based signal processing systems. In this lecture, we'll do the infinite impulse response filters. What is the design and how to develop this Verilog module? What are the types of infinite impulse response filters and so on in this week. So IIR filters, when we started with the FIR filter, we have learned the what is the difference equation obeyed by this FIR filter. In that FIR filter, we saw that there is a input xn and output yn. The output yn is depending on the present input and the past inputs alone, xn, xn minus 1, xn minus 2 and so on. But in case there is no feedback involved in the FIR design, that means there is no y of n minus 1, y of n minus 2 is taken to decide the current sample output. But in case of IIR filter, we have at that time itself we had differentiated that it would take present input, past input as well as past output samples to decide the present output. So the difference equation obeyed by this IIR filters are y of n, the current sample or present output, is depending on the first feedback y of n minus 1 and y of n a1 in a2 into y of n minus 2, a3 into y of n minus 3 and so on up to a of n minus 1, y of n minus 1. I stopped over here. So this is for the past number of samples of the output n minus 1. This is the current output. This one is the previous one output of the output current and the output, and then past samples of the outputs are taken in this plus. And then similar to the case of FIR filter, we have a coefficient x of n, if you recall, b0, b1, b2, bn, bn minus 1, and that is present input, past inputs n minus 1 up to what is the tap delay we used in the FIR filter. So this portion is similar to the feed forward. This is called the feed forward coefficients of the IIR filter, and these are a1, a2, an minus 1. Those coefficients are feedback coefficients. So b0 to bm minus 1, a1 to an minus 1. How do we get these coefficients is the design of the IIR filters. So now we can take the z transform of it, that would result in y of z equal to minus a1 z minus 1 y of z minus a2 z minus 2 y of z minus and so on, and then n minus 1 z power n minus 1 into y of z. So the first part plus, if you take the b0 x z plus b1 z minus 1 z power minus 1 x of z plus b2 z power minus 2 x of z and so on up to bm minus 1 z power m minus 1. So simplifying all, taking all x together from this term and this all y together from this term. So if you bring it to the left hand side, this is actually the y of z by x of z, that is equal to the h of z. Okay, so x into x in x of z into b0, b1, b2, you can see that. Also y of z into these coefficients you have. If you push this to the left hand side and then one side, and this will be equal to the, so 1 plus a1 z power minus 1 is, so this decides the order of the filter. And then these are the numerator polynomial gives the zeros of the transfer function, and then the system itself, the IIR filter, and the denominator gives the poles of the system. So the IIR filters, so it has zeros and poles. Okay, so the getting this coefficients is the design, or getting this transfer function based on the specification is the design of the IIR filter. Coming to the, we can also simplify the taking z bar minus m minus 1 to this side and then adjust the coefficients and getting this in terms of z m minus power 1 and z is n minus 1 to up to this coefficient. That is also a form of h of z. So getting after this, what are the little comparison what we know from FIR to IIR filter. This is a complicated structure which has this past outputs also in the equation. So it has a feedback structure and doesn't exhibit linear phase characteristics. If you recall that pass band, we have this phase which is linear and the coefficients which are giving the linear phase characteristics, and compared to the order, it is having the reduced passband ripple, good characteristics of the filter. Also, filter order is less compared to FIR, meaning for the given specification, if you design an FIR and an IIR filter, the order of the IIR filter will be lesser than the FIR filter for the same, to get the same characteristics. And so multiplication per output sample is less to FIR. That means to get the Y of n, the multiplication would be less FIR. And then a sharper filter roll off will be roll off rate of the filter is good. For given number of multiplications per output sample, this IIR gives the better filtering. If you take the multiplications per output sample in the hardware, which is very costly in the DSP, so the multiplication per output sample, if you compare for FIR and IIR, this gives IIR gives the better filtering. So the structure of the IIR and filters, FIR filters, we had this linear phase and direct forms also. So here I'll see the IIR scale. Suppose taking this the three coefficients in the numerator, and this, or let's consider this is 2 is the L minus order here. So take this polynomial. If you have this coefficients b0, b1, b2 and 1 plus n, a1 and a2, in this case how we get the structure for it. So for example, to decide this multiplication and additions and delays used in the structure, taking the numerator separately and the denominator part, the cascaded version of this h of z, numerator and the denominator, we have this call this numerator polynomial as h1 of z as a transfer function, and h2 is another transfer function. This is a cascaded transfer function, which is the convolution in h of 1 and h of 2. Okay. So here, if you take this h1 and h2, so we can consider it in two ways because it's a cascaded cascaded form. So h1 of z cascading with h2. So x of z is the input to the filter, y of z is the output, and here is w of z is the intermediate result of h of 1, and which can also be written like or are expressed as h2 into h1 as well. So h2 and then h1. So cascading can be either first to push this h2 first and then h1 later. So that would also be so. So two ways this structure can be developed. So we'll see how this is, if this is h2, so this is the h2, y of v of z by x of z is h2, and h1 is y of z by vc h1. So this is the one h1 and this is h2. So we'll keep this h1 and h2 as such and just interchange this positions and see the structures of that. Form 1, direct form 1. So first case h1 of z is w by x, which is giving the numerator, and y by w is giving the denominator. So if you get this w of z from this, y of z equal to, so y of z, multiply this thing, and which is equal to w of z. Okay, so from the h2, and then so yz equal to wz, and y of this y you bring it this side. Okay, so the right side, a1 a2 is at y of z. So this equation can be obtained from here. So these two, push them to the right hand side. So from that one, we get one equation here, y of z equal to w of z minus a1 z bar minus 1, a2 is delay 2 y of z. And considering the w of the numerator, see here, this is the numerator, w is equal to this polynomial into x of z. So from this we can obtain one equation, and the last equation from the second H2 we can get Wz minus this. So how we are going to realize this? So x of z, take this one, and then you can see x of z multiplied by b naught is the this path, x of z multiplied by b1 z minus 1. So delay this xc and then multiply it. This is the second path over here, and the third one delay it once more, that is x of z is delayed twice, and then multiplied by b. Add them. You can have a single adder or multiple adders if two inputs, so on. So this is the function one which is giving the realization of w and x relation. Okay, so whereas this one y of z here equal wz we have here, and then y of z, that is a past output delayed and multiplied with this coefficient. You see the negative coefficient and added, and this is y of z multiplied with a2 and added over here, so which gives y of z. So this particular polynomial or this expression is realized in the right hand side. So this is the cascade connection of H1 and H2. Okay, so this is giving the feed forward network, we feed forward coefficients as well, and this is the feedback network or the feedback coefficients A1 and A2. So this is one realization which is having multiple delays and the coefficients and adders. So from the second one, H2 and H1 can be interchange the two. The given transfer function, the numerator multiply this y of z, directly take this as y of z equal to this into v of z. Okay, multiply this by v of z, and then xc denominator, that is directly take this, not a 1 by of this xc into v of z. So from this vc equal to xc minus, so here you can have this expression from here, and this is another expression. So from this is the structure. So x and vz, here x, you can observe this vz here, also this one, a1 and a2. So first come the feedback xc and vc is at the center, delay it minus a1 and add it to this to get the x of z plus this. Okay, and then delay twice, and this is h2 of z, and the same hc delay it further, and what is b naught as such, and b1 b2, this is the numerator polynomial h1. So now these two are exchanged here. This is the feed forward one, and this is going to be the feedback structure. So feed forward, which was in the left side, has now become the right side, and the one which feedback part which was in the right side has become left side. So still you can see the v of z is the same point which we are tapping it twice through the delays. Almost this and this are same, and this is also same. The signals we got is that delayed vz delayed once and then delayed twice here. So from this we have the redundant delays which can be combined into one delay to have the less number of delays in the structure. That's how this direct form 2 helps in to get this, combine this delay at this point vz xc b0 b1 b2 minus a1 a2, so y. So this is the IIR direct form 2. The redundant delays are made one delays here. So that's the advantage of exchanging this h1 and h2. So feed forward coefficients are here and feedback coefficients are here. So you will get the same outputs, only the saving of delays in this case. If the order is same, be here numerator and denominator polynomial are equal, then delays will be equal. Otherwise, which side you have, suppose this has more delays, then you need to have one more delay over here, or if feedback has more delays, then it will contribute to one more delay and multipliers here. Each coefficient needs a multiplication. So as we have seen in the FIRs also, coefficient needs to be multiplied by the input. So like the delayed output here, this vz should be multiplied by the coefficient and added to it. So it depends the number of adders, multipliers and delays. So delays are getting reduced in this form compared to the direct form 1. Feed forward and feedback coefficients. So generalized form of this direct form 2 structure is this b naught. So how long we have to extend, how many delays we will be using it. Okay, so a1 b1, this is b naught, the first coefficient in the numerator, and then it goes up to the numerator bm minus 1. What was this coefficient, or bm, what would be the last coefficient, and a1 n minus 2 to an minus 1, this is the coefficient in the denominator. So adding up, this is a generalized structure of the, so which would go here and this would go this side, like. So this is a generalized direct form 2 structure. So form 1, direct form 1 and 2 structure, the 2 has the delay, number of delays less compared to the redundant delays are reduced in that compared to the direct form 1. So now coming to the filter design. So in the filter designs, digital filters especially, we can design in 2 forms generally. It can be designed. One is we design a digital filter in the digital domain itself. Specifications and other things are given in the digital domain itself, and or we can have the specifications in the analog domain as analog filters. Specifications are given in analog domain and then design the analog filter. So we have this analog, design the filter in this, design the filter in the analog domain, and then convert them into digital filters, that is through mapping. Okay, so that mappings can be, for example, this is the type of filter design we'll be going to use it in the IAR filter design. In that case, we need to have the specification and other things in analog domain, and then the design is done in the analog as analog filters, so Butterworth and Chebyshev, and then use the transforms or the method to discretize it, the analog filter which is designed to be like an impulse invariance method, or that could be a bilinear transform. So these transforms can be used to get the discrete version of the analog filter. So this design involves this analog as well as the transformation. Or the specifications which are given in analog needs to be directly transferred to the digital domain, or equivalent in digital domain, the specifications, and then design that in the digital domain. So that is another form of designing the digital filters. So here we will be looking at this IAR in this fashion. Also, once this analog, we can use this another frequency transforms as well. For example, so low pass filter is designed and then want to convert that into high pass filter, high pass, or from low pass to band pass and band reject. So frequency transformations can be used in those also. So that is another way of getting the filter designs. So here the analog filter, will be looking at this Butterworth and Chebyshev in this week filters, and then get the discrete version of it through impulse invariance method or bilinear transform method. What is the difference between them? How this the S to Z mapping happening in this impulse invariance and the bilinear transform methods. What is the impulse invariance method? It is just to like to give the few details. Suppose we have this analog filter which has the transfer function hc of s. S is Laplace variable. Have the Laplace transform of the filter, that is the transfer function hc of s. If you give the input x of t as del of t, the impulse input as shown here, continuous time impulse input, and the analog filter would respond and give the hc of t, which is the impulse response of the analog filter. And in the, what is the digital IAR will do here, that we have to find the equivalent of hc of s, equivalent of this as h of z. So that is the transfer function of the digital filter. How these two are related is, if you give x of n, the discrete version of this input x of t xn, so which is the del of n, the input here, which is the impulse input, and the other things are here 0 anyway, we can say the impulse input, so 0, these points over here just 0, and the output what we get for the discrete impulse is the h of n, the impulse response, which is sampled version of the continuous time impulse response what we got through this analog filter. So we have this is going to be sample this filter at a particular time instance or the sampling time given Ts. Okay, so the difference between this one sample to the other sample, suppose this is the first sample, second sample, this is going to be Ts, sample time. So digital IF filter is a sampled version of the impulse response of the analog filter. Okay, so this is what we are going to design. So conversion from this to this is one design in the impulse invariance method. So how we'll be doing that operation is that first case is analog filter is the desired frequency response. The specification, everything is given in analog, and then IR filter is the discrete approximation of that desired response in the analog. So the mapping used is z is equal to e power st. So hi of s, that s is replaced with this, s is equal to here s will be replaced with a formula that the relation is z equal to what is the mapping between e power st to z. That mapping we will see in the next class, but the mapping used is z equal to e power st. From this, just would like to list the steps involved in that design of the impulse invariance method. So the first is design the analog filter HC of S for the given specification, get the transfer function of the analog filter in the with the Laplace variable, Laplace transform of it. Yes, and then impulse response of HC of S. Okay, so get the impulse response of this, that is through inverse Laplace transform. So inverse Laplace transform of the transfer function what we have got in the analog for the analog filter for the given specification is HC of t. So this is inverse Laplace. Once you have the transfer function of the analog filter in the with the Laplace variable, then get the impulse response of it, that is HC of t. So have this HC of t and then determine digital filter sampling frequency Fs. So from this HC of t, what should be the Ts used to sample this response. Okay, so the impulse response I have shown in here. Here we need to know the Ts here. So once you have this HC of t here, from this H of S, and through the specification given, get the Ts value, determine what should be the Ts value for this to be for the response to get digital. So from that Fs, you will come to know the Ts 1 by Fs, and then find the Z transform of Hc of t, which is again the continuous domain. So we need to take the Z transform to get H of Z. H of Z is, you can see the two transforms from analog to digital, or if you know the Z transform of it directly from S to Z, transformation can also be applied, the two tables, skipping the S and Z here. So inverse Laplace and then Hc of t, that is the impulse response of the analog filter, then get the Ts value, that what is the sampling frequency should be, and from that using the Hc of t, get the Z transform of it, H of Z. So H of Z is nothing but the filter which we need it in the discrete version. The discrete version is this is the discrete version of HCS. So this transfer function in Z domain gives the filter with the coefficients and all. And if you want the time domain equation of this, y of n equal to minus a1 y of n minus 1 minus a2 n minus 2 y of n minus 1 a n minus 1, that's the difference equation. Get this, don't forget to put the t, all the t here, that means t is to t here. Ts value is what we have used to t, convert this to t, and then inverse this conversion will see why is it important in this case when we design one of the filters, and then have the inverse is the transform so that you can get the y of n for it. Okay, so inverse C H of Z is known, and y of n in terms of x of n, you would get this so that the coefficients can be here. This itself will give the transfer function, it's the Z domain transfer function itself will give the coefficients, a set of A co-feedback and the set of B coefficients on the feed forward coefficients. So this is of the impulse invariance method, but would like to show the mapping and what is the aliasing which creates the problem in the impulse invariance, and how the bilinear transform method would be better in this case. What is the how we use this bilinear these transforms in the when we know the analog filter prototype. If it is known, then it is easy to get it one inverse Laplace, and then one Z transform would give the digital filter IIR. So this would be, once we have this equation, we can have the coefficients of A and B that can be used in the Verilog module to have these coefficients like what we have done in the FIR filters. The Verilog module can be developed with these coefficients, and then especially we could see this, that is in the H of Z we can see there is a feedback structure involved in it. So we would design the filter of using impulse invariance method, and then the bilinear transform method of IIR, how the transformation is used. Also, we look at what is analog filter process, or the step design process of Butterworth and Chebyshev in the next lecture. Thank you.